Hi, everyone. Thank you for having me. This is definitely a unique opportunity. I'm from San Diego, California, United States, and so being able to attend a conference like this that normally would have taken place in Germany, just a unique opportunity. I'd also like to put a shout out to my friend Yana Mohanty. She was the one who really put this in my mind that, hey, this really is a unique year, let's say. And not often I get to attend. So thank you for having me. I appreciate it. So as I said before, I'm David Honda. Here's some of my contact info if you'd like it. I'm a middle school mathematics teacher. My email and website I keep is right there. I keep a lot of my Snapology projects. And as was mentioned by Martin, my presentation is on Snapology. For me, what I'm hoping you get out of this is a way to play with math. For me, I'm definitely coming at this from the art perspective and branching into math. Now, growing up, I used to do a lot of origami. I'm gonna take this down because it's covering my face here. And so, I always grew up doing a lot of origami around the house. It was just a hobby of mine. And so eventually as an adult, I got into a lot of different paper crafts. I consider myself a maker. I do laser cutting, paper, woodworking, 3D printing. And so then when I came across Snapology and the fact that one of my other passions is mathematics, that I found those two things crossing. I found a crossroads between the two. So for me, what I'm hoping you get out of this is possibly a new hobby, that Snapology is a great way to explore mathematics. And the title Big Boy Blue, I'll show you in just a sec, but what I'm hoping to do here is talk a little bit about what Snapology is exactly. I'm not going to go through a full-blown demonstration, we don't have the time, but just really quickly kind of describing that, talk a little bit about the project Big Boy Blue, and then show you some other, kind of my journey with Snapology and how it's opened up a lot of areas of mathematics for me. As a middle school math teacher, 20-something years, I've day in, day out, it's, solving two-step equations and geometric transformations, and I don't often get to play with higher levels of mathematics. So first, a little bit about Snapology. I first came across the work of Heinz Strobel. He's the originator of Snapology. And if you ever look him up, his projects are amazing. They're beautiful pieces of art. And what's really unique about them is, much like traditional origami, there's no glue or tape or any kind of adhesives. It's just strips of paper folded, cut, and put into interlocking units. If you are interested, also, there's one woman, I've met her, she's a very nice lady. We talked a lot, Faye Goldman, she's written a book on this called Geometric Origami, and it's a way to get started. Oh, and before I forget, when Heinz Strobel, at least from his websites, he calls it Snapology. If you are interested in this, what I would do is search online for Snapology Origami. If you only search for Snapology, you end up getting a lot of the name's been trademarked by a lot of Lego clubs for kids. So anyway, so I thought I'd start off by kind of showing you what Snapology is exactly, so you could have an appreciation for some of these projects here. So I'm going to share my screen. If I do this right, you should be able to see my document camera. Is that working okay for everybody?
Yeah, that works perfect. Thank you.
Okay, great. So the idea is this, is that all I have is strips of paper. For this demonstration, I'm using 1 inch. You could use anything. I usually do more like 1 centimeter. But the idea is fairly basic. And that's what I think I really liked about this, is that getting started is fairly simple. So what you do is you take 2 strips of paper and you fold one around the other. You just tightly wrap it, trying to keep everything as perpendicular as possible, nice creases. And you eventually get to a point where you've got enough. And so if I unravel this, what I'm shooting for here is just, in this case, I'm trying to make a triangle. So I'm going about, I call this, for my demonstrations when I do workshops, this is 1 unit. So I'm going about 4.5 units. But long story short, all I'm really trying to do is create the surface of my shape. So in this case, this would be a triangle. and just the overlap holds it all together. So I'll make another one of those. And like I said, don't worry, I'm not going to spend the whole time doing this. Normally, when I do workshops with kids or even adults, usually takes about an hour and a half to complete a project. So I'm just kind of showing you the basics of what the process is. So there's my two triangles. And then in a much similar fashion, excuse me a moment, just got to get some paper. You make what I call connector pieces. Same thing. And again, for me, this was the appeal. It's a very simplistic start to make the units. But you just fold. The only difference this time being that what I'm shooting for here is a length of 4 units. And so I get this piece, and this will serve as a connector. And so when I do this with my middle school students, we kind of do it as a fun exploration into geometry. We start talking about vertices and faces and edges. So what they'll do is they'll take their two triangles, hold them side by side, and then I always refer to the connectors kind of like a staple. This does exactly what a staple would do. It just punches through the paper and closes up. So same thing here. You take the staple, the ends punch through the, punch through the triangles, just right through the big triangular openings, like so. Push it all the way through just like a staple would. And then if you think what a staple does with that plate on the other side is it takes the ends of the staple and bends them inwards. So what I do here is I open things up a little bit, and then these bend down. And so this is the basis of Snapology. It's just this making the pieces and doing this one connection piece is really all you need. But if you imagine just, sitting there in front of the TV and taking it to the nth degree, you start building things. So this would be 5 of the units put together and eventually getting something like this. So this is what I do with my middle school kids. We talk about the different geometric solids. Specifically here, we've got an icosahedron. It's a little hard to see it because you've got these triangular prisms sticking outward, but if you kind of visualize it, at the core is an icosahedron. So for the level I teach at, this is a great exploration in terms of geometric solids and the language that goes along with it. And it's just kind of a fun little art project for my students. So let me get back here just a moment. I'm working off 2 different monitors, so I'm trying to keep it all straight here. There we go. So that's a bit about Snapology. So hopefully that'll kind of give you an appreciation for Big Boy Blue here. So Big Boy Blue came about, as I said, for me, this was a passion. And for me, honestly, I wasn't looking at the mathematics. I was strictly looking at this as from an art or even an engineering point of view, as I started to make shapes like this, but larger ones. So larger, like sphere type shapes. And I asked myself the question, could I build something with an internal structure? And so that's where Big Boy Blue came into place. So let me get rid of that real quick. So I'm hoping you can see this. Ugh. But this is Big Boy Blue. It's dodecahedral shape, 11-hole torus. But as I said, I think the interesting part for me was I was looking at this more from a art perspective. I was just trying to create something with an internal structure. And it wasn't until I met my friend Yana Mohanty, who also had a passion for specifically geometry. We just started to delve into conversations about tori, about positive and negative curvature, the construction of this. We started talking about saddle points. And for me, that was the moment I realized that this could really be a way for me to explore mathematics, that it wasn't just about creating something out of paper or creating some art, but it was a way for me to play around with mathematics that I don't normally get to work with on a daily basis. As I said, I'm a middle school teacher, so things like topology and fractals, I don't get a chance to play with that much. And so for me, this was great because it just gave me a way to play with things. So a little bit about Big Boy Blue. So you can, it's hard to see, if you were here, you could take a closer look. But essentially, Big Boy Blue has an internal dodecahedron, and then an external one. And what's joining them together are kind of like these tubes that cross from the inside to the outside. So starting here, this is an internal shot. I wish I had taken a picture prior to this, but I've kind of outlined it. So right here, you can see one of the pentagonal panels that makes up the dodecahedron. And so if you imagine that, imagine a pentagon, a flat pentagon, but rising up out of the middle of it is kind of a volcano shape. That's what you're seeing here. And then of course, 12 of those fit together. And then this is at the core. So inside Big Boy Blue, this is what's holding everything together. And then from these areas that you see there in white, that's where I continue to build. And so if you look here, this is Big Boy Blue partially done. And you can, if I zoom in here, you can see where I've extended one of the columns outwards. And then as it extends outwards, it kind of flays out like the top of a funnel. And of course you get Big Boy Blue. So this is what I presented to the committee as far as my proposal. But again, this talk wasn't so much about Big Boy Blue as it was, again, trying to share my passion for Snapology and how it really opened up some avenues for me when it comes to mathematics. So let me see here. I get lost in my presentation sometimes. So for me, my journey was I started off where kind of logically thinking that where you might is just polyhedra. Some of the shapes I've kind of brought to show. You saw the icosahedron earlier, but then I thought to myself, what if I started to vary the width of the strips I was using? Well, it turns out that it actually came in very handy for my class because I went from something looking like this, where it's a little hard to see the polyhedra, to more of a wireframe model. So now I had a cheap way to do wireframe models to, pass out to my kids, and they could just actually touch the mathematics, similar to the presentation we just saw with the 3D printing. I started to investigate more from an engineering standpoint, which shapes would give me more rigid structures, whereas this dodecahedron, which I made, had more of a flexible quality to it. Also, again, varying the width of the strips just gave me places to play. So like here, this is it's not quite the same, but it's basically a truncated icosahedron. It's a little hard to see because the hexagons are made of triangles. But then what if I change the strips? This is the exact same model, but it ended up looking completely different. Started to play around a bit with fractals. I'm going to move this out of the way here. It's a little hard to see with it taking up most of the screen. Now, of course, I'm not brave enough to try anything as extreme as like a Mandelbrot set, but I stuck with Sierpinski's triangle, and so this model sits in my classroom, and for me, it builds a lot of interest for my kids. They're like, oh, what is that? How was that made? What is that design? And it's an opportunity for me to talk to the kids about some different branches of math that we don't play around with in class. It's just a way to build interest. They walk into my classroom, they see these things, they're like, wow, Mr. Honda, what is that? Later on, again, talking with my friend Yana, we started talking a lot about topology. So I started playing around a lot with tori. And so other ones like Big Boy Blue, this one was kind of a different take on that. And here's a recent one. So I started to play around with what if the edges of my shape were something other than just a straight line, and instead, what if they were like joined circles? And this one got me thinking about like protein structures and how those look, or molecular models. And so again, it was just it's hard to imagine, but what makes this up is what makes this. There's no difference. The pieces and the connection is the same. It's just, this is a fun hobby. This is just saying I've got too much time on my hands. And then, how am I doing on time here? A few others. I started to play around non-orientable surfaces, and so specifically looking at a Klein bottle. Now this is an early prototype, so it doesn't look that great, and I'm still working on it, but this was my Snapology version of a Klein bottle. The bottle, you know, going into, changing into its neck, the neck going through the structure, and then coming out the other side, then forming the bottle. Still not happy with this one, but working on it. But again, I don't think I would have played around with this unless I had learned Snapology as a way to do this. This one's a more recent one. Once again, my friend Yana, we talk way too much. I apologize for the noise. In distance learning with my middle school kids, I'm teaching from home, and with a 3-year-old and a 6-year-old at home, I got kicked out to the garage. And so I'm going to hold up a sec, because right now I don't know if you can hear it, but there's a garbage man outside and the truck's making a lot of noise. The perils of distance teaching.
It's actually pretty fine from our side. So
okay, I'll keep going then. So this one, just interlocking pieces, and wow, I just blanked on the name. Borromean rings. There we go. And so again, just being able to take, you know, an art passion that I have, but to explore mathematics with it. And then I started to go beyond mathematics. I started to look at things in biology and chemistry and engineering. So for example, totally happenstance, but after I did Big Boy Blue, I happened to be looking around and looking at things like dodecahedrons, and I came across this picture. And this is a microscopic view of pollen. And I thought, wow, that could be interesting. I could then go in and explore, you know, different types of, you know, cells and molecules and things like that. Maybe that'll give me my next inspiration. I started to look a lot at Buckminster Fuller. He's done a lot of work with geodesic domes, the buckyball, the carbon molecule, which is right here. And so again, just giving me a chance to play in fields and subject areas that I normally don't come across in my daily life. Now recently, my recent work, what I'm playing around with is the fact that shapes like this are mostly made up of triangles, equilateral triangles. So getting certain shapes is kind of difficult. So I try to challenge myself and do something more 90-degree cubic in nature. And so this is some of my recent stuff. I apologize for this first one. I don't know why every time I do it and test it out, works fine, but then I broadcast it and this comes out sideways. So I apologize for that. So this was one this is my attempt at trying to make something cubic rather than a round shape. And then my most recent one, which I'm very proud of, this has found a home at the University of Pennsylvania. We named it Cubic Fusion. And it's 4 cubes joined together. And then the copper part you see is the intersection of those 4 cubes with an invisible sphere. And so this one just made its way to University of Pennsylvania. And so that's basically Snapology. That's what I was hoping to share with you. But again, what I'm really hoping you walk away with here is just maybe you'll pick this up as a hobby, that if you finish up with the conference and you look this up and you find the time, this for me was a great way to explore. And I'm hoping for my kids too. In fact, a story I kind of want to end off with is I recently moved, and down the street, I happened to meet one of my neighbors, and it turns out that one of my neighbor's sons was a former student of mine. And this is like 10 years later. And she tells me that to this day, he still does Snapology. He remembered it from my class, and he uses it as a way to just, make different shapes and explore as well. So I'm kind of hoping for some of you that this might be a spark that kindles you into a new hobby, and hopefully a way to just play with the mathematics. I think that's what I enjoy the most. It gives me the opportunity just to explore and play. I don't know if I want to, I don't know if I get the 5-minute warning, if I should just open it up for questions now.
We can start with the questions. So you have 4 more minutes, or we can just start with the questions. But
okay. I'd say the only other thing I was kind of, I don't know if I was actually looking for suggestions from this group, is the one thing I've always wondered about some of my projects is, is there a way to figure out, are these truly, in terms of mathematics, are they truly shapes that can be created? Or, because there are some that I make, like this one. And I wonder, is there a way to test whether or not, like with actual, like, I guess computer modeling, I would say, with actual rigid shapes, could this actually be created? Or am I kind of getting away and bending the rules of mathematics a little bit because I'm working with paper, and paper can flex and it can bend. And so maybe this isn't a mathematically accurate model if put to, you know, a computer graphics, into a computer graphics model. So for me, that's been a big one that I want to explore, but I just don't have the resources to do it. So, but yeah, I think I'll stop there.